Hi, today we're going to talk about Young's modulus. Young's modulus, that we call E, is a property of the material that corresponds to how much it will want to compress or stretch when you put it underneath a load. So basically we call it sometimes the stiffness of the substance. Underneath tensile strength, tensile means we're pulling, compression means we're pushing it in. Now Young's modulus is measured in, well, the unit is pressure. It's either in pascals or newtons per square meter, but 1 pascal is equal to 1 newton per square meter. So the two can be interchanged with each other. And epsilon, that's kind of a small font, but E is equal to sigma over epsilon. And we use sigma a lot for a lot of different things. This time we're using it for pressure. And epsilon, again, we use for a lot of different things, but in this case, it's actually dimensionless. Because sigma is the force we apply to it divided by the cross-sectional area of that material. Usually it's a cylinder or a square or something like that. And then for epsilon, that's the change in length, so how much it's stretched or compressed, divided by the original length. So we're going to look at 3 examples. 2 where we're going to find how much it's stretched, and 1 that we're going to figure out what the Young's modulus is for that material. Okay, let's take a look at our first problem. We've got a 2-meter long aluminum rod, has a radius of 3.5 millimeters, a modulus of 69 times 10 to the 9th newtons per meter squared, and the cross-sectional area is a circle, so that's important. And we've hung a 25 kilogram mass at the bottom of it. We want to know how much it will stretch in millimeters. So we've got our rod. Originally the length was 2 meters, and we have attached a mass of 25 kilograms to it, and we want to find how much it stretches because we attach that mass to it. So the first thing was Young's modulus is E equals sigma over epsilon, where sigma is kind of the pressure you've put on it because you've attached this mass to that bar. This is the modulus, so this is consistent with aluminum. And epsilon is the change in length divided by the original length. And we'll get that in a second, but first I want to figure out what sigma is. So to do that, I need to first figure out the cross-sectional area, because sigma is force divided by area. And so I want to figure out the area. So our radius is 3.5 millimeters. Now I want to change that to meters, so that's 0.0035 meters, because we want to keep our standard units. Usually our standard unit is meters, kilograms, that such. So I want to get it out of millimeters and put it into meters. And then I want to find the area. Well, the area of the circle is pi r squared. I'm just going to use 3.14 for pi in this example. And we're going to square the radius. So 0.0035 squared times 3.14 gives me an area of 3.85 times 10 to the minus 5th meters squared. So that's our radius. The force we put on there is the weight of that 25 kilogram sphere. So I want to figure out the weight of that object. Weight's mass times gravity. And I'm going to use 9.8 for gravity. And we get 25 kilograms times 9.8 meters per second squared gives me a weight of 245 newtons. So that's the force we've put on this. So to find sigma there, I want to take my 245 newtons and divide by the area, that should be an A, of 3.85 times 10 to the negative 5. 3.85 times 10 to the minus 5. And we get sigma to be a really big number. So I'm going to kind of round this off a little bit. 6.36 times 10 to the 6 newtons per meter squared. So that's what sigma is. Now what we can do is we can actually figure out what epsilon is. And so let's do it over here. Epsilon is equal to sigma, E is equal to sigma over epsilon. E is 69 times 10 to the 9th. Epsilon is 6.36 times 10 to the 6th. We got to figure out what epsilon is. Swap places with it. Epsilon comes out 6.36 times 10 to the 6th divided by 69 times 10 to the 9th. Let's see what we get. 6.36 times 10 to the 6th divided by 69 times 10 to the 9th gives us epsilon of 9.22 times 10 to the minus 5. And that's a pure number. It doesn't actually have a unit because we're taking a length divided by a length. So the units actually cancel. So now that we have that, we can figure out how much it will stretch by using that equation. Epsilon equals the change in L over the original L. So 9.22 times 10 to the 5th. The change in length we don't know, but the original length is 2. So 9.22 times 10 to the minus 5 times 2 gives me a change in length of 1.84 times 10 to the minus 4, and that's in meters. Well, if I rewrite that, take it out of scientific notation, I get 0.000184 meters. But I wanted the answer in millimeters. So I moved the decimal place over. So the change in length is 0.18 millimeters. So that's how much the length of that rod would change because we added that mass to it and put it underneath some tension. Let's look at another one where we have a slightly different cross-sectional length and compare the two. So we're going to use the same length bar, but this time we're going to change the cross-sectional area to a square. All right, so same picture. We've got our mass on the end of our rod. Rod's original length is 2 meters. This time it's a square. I'm not very good at drawing, so we're going to stick with that. The mass is still 25 kilograms, and we're still looking for the change in length. Now this time it's a square that the side is the same as the diameter of the rod. And so we're going to see how that compares because the square would have, as a cross-sectional area, the square will have slightly more material than the circle would. So that rod will have a little bit more matter to it than the rod would. We still have E equals sigma over epsilon. And I still want to go ahead and start off by finding epsilon, which is force over area. Again, I want to start with the area. And we've got a side of 7 millimeters, which is 0.007 meters. And since it's a square, we're just going to square that number. 0.007 squared is 4.9 times 10 to the minus 5 meters squared. So that's my area. The force is still the weight of that 25 kilogram mass that we put on there. Again, I want to use 9.8 meters per second squared for gravity. And we still get 245 newtons is the weight of that mass that we put on there. So let's find sigma. Sigma would be 245 divided by 4.9 times 10 to the minus 5. So 245 divided by 0.9 times 10 to the minus 5. And we get sigma of 5 times 10 to 46 to the 6th newtons per meter squared. Or you could call it pascals if you wish. Now that we know that, we can figure out what epsilon is. That's 69 times 10 to the 9th. Sigma is the 5 times 10 to the 6th. We can find epsilon. Switch those out. 5 times 10 to the 6th divided by 69 times 10 to the 9th. And we get 5 times 10 to the 6th divided by 69 times 10 to the 9th. We get this to be 7.25 times 10 to the minus 5 is our epsilon. Again, it's dimensionless. Now we can find how much it's stretched. So that's 7.25 times 10 to the minus 5. Delta L we don't know, but the original length was 2 again. So 7.25 times 10 to the 5th, negative 5th, times 2 gives us a change in length of 1.45 times 10 to the minus 4. But again, that's in meters. So I want to change that to, well, I'll take it out of scientific notation, 0.00014 meters. And then I want to convert it back to millimeters. So I move the decimal point over 3 spots. So that becomes 0.14 meter. So it doesn't stretch as much. The other one stretched 0.18. This one stretches 0.14 because there's more mass there. There's going from a cross-sectional area of a circle to a cross-sectional area of a square with the same radius. Then you've got this extra material here that keeps it from stretching as much. Let's do one more example, and this time let's actually figure out what Young's modulus is. All right, so now we've got a 4 meter long rod. So we're back to a rod, cross-sectional area is a circle. Radius is 5 millimeters. And we've attached a 200 kilogram mass to it, and it's stretched 2 millimeters. So let's see what we can do with this one. So we got Young's modulus equals sigma over epsilon. This time we're looking for that, so we're going to hold off on finding that. Let's first figure out the cross-sectional area, because we need to do that first. So the radius is 5 millimeters. Again, I want to change that to meters. So that's pi r squared. So 3.14 times 0.005 squared. Let's see what we get. 0.005 squared times 3.14. 7.85 times 10 to the minus 5 meters squared. That's our area. And this time we have attached a much heavier mass to it. Or a much bigger mass, which is also going to be much heavier. Mass times acceleration due to gravity, so that's 200 times 9.8 meters per second squared. So 200 times 9.8 gives me a force of 1960 newtons. And so now I can figure out what sigma is. So sigma is going to be force over area. So in this case, it's 1960 over 7.85 times 10 to the minus 5. So divide by 7.85 times 10 to the negative 5. And we get sigma to be, again, I'm going to round off a little bit, so that's 2.5 times 10 to the 2467 to the 7th newtons per meter squared. 2467, yes. So we got sigma. Now for epsilon, we know it's stretched 2 millimeters. So again, change that to meters. So that's 0.002 meters. So we got change in length over the original length. So that's 0.002 divided by the 4 meters, which was the original length. So 0.002 divided by 4 gives me 5 times 10 to the negative 4. Again, that's dimensionless. So with all of that, we should be able to figure out Young's modulus for this material. Sigma over epsilon, so sigma was 2.5 times 10 to the 7th. Epsilon is 5 times 10 to the minus 4. So 2.5 times 10 to the 7th divided by 5 times 10 to the negative 4 gives me a modulus of 5 times 10 to the 10th newtons per meter squared. Thanks for watching. Please subscribe and like the video if you want more content, and I will talk to you later. Goodbye.